so may I start?
Yes,
Oops, sorry.
please.
Okay, so it's just going. All right, so I hope I will be able to stop it. Okay, so first of all, I would like to thank the organizers for giving me this opportunity to give my talk uh, from uh, from home, essentially. And I'm really sorry that I was not able to join this very nice workshop and to see all the friends in this field. Today, I'm going to talk about work that is almost finalized with Carlos Hoyos, which was conceived over the last week of a workshop that we had in Florence about relativistic hydrodynamics. And the topic is a pseudo-gauge-invariant local thermodynamic equilibrium density matrix, which somehow connects to something which has been brought up by Maxime in his talk, so pseudo-gauge invariance. And I will be, so after a short introduction about what pseudo-gauge invariance is, then I will tell you what is the problem in heavy ion collisions about this pseudo-gauge invariance, and then our proposal of a new density operator which represents local thermodynamic equilibrium and at the same time does not suffer from pseudo-gauge dependence. All right, so let me, if I manage to start, yes. Okay, so in quantum field theory in flat spacetime, there are two conserved currents coming from the invariance of under translational and Lorentz transformations. The nether currents are well known. They are the stress energy tensor and the spin and the angular momentum current. The angular momentum current is made of an orbital part and a spin tensor, which are written here. So these currents, as you know, they fulfill the conservation equations. And then, which means that energy momentum and angular momentum boost are conserved. However, as you may know that the Lagrangian density is not uniquely defined, therefore this Lagrangian can be changed, and so those tensors can be changed as well. Indeed, more in general, if I manage to, sorry, I have a problem in scrolling the talk. All right, so more in general, the stress energy tensor and the spin tensor can be changed by a so-called pseudo-gauge transformation. If phi is a field which is a tensor of rank 3 antisymmetric in the last two indices, then T mu nu and S mu nu can be, and S lambda mu nu can be changed by means of this transformation. And this transformation leaves the conservation equations invariant, so T prime and J prime fulfill the same equations, and the integrals, namely the generators of the symmetries, are left unchanged. So the integral over any hypersurface, 3D space hypersurface of T mu nu and J mu nu lambda nu is the same. Okay, so this makes the definition of stress energy tensor and spin tensor somewhat arbitrary. And indeed, this can be taken advantage of in order to, say, for instance, to get rid of the spin tensor altogether. This is the so-called Bell-Infante symmetrization procedure. So one can choose a superpotential which is precisely equal to the spin tensor obtained from a Lagrangian and get a new spin tensor which vanishes, and at the same time T prime mu nu gets symmetrized. For instance, for the free Dirac field, from the mostly used Lagrangian, one gets a stress energy tensor which is non-symmetric, which is gamma mu, the new bidirectional psi bar psi, and the spin tensor which was mentioned in the previous talk by Maxime. By using this symmetrization procedure, one can get rid of the spin tensor and obtain the Bell-Infante pseudogauge, a completely symmetric T mu nu, and a vanishing spin tensor. So the morale of the story is that which is the traditional wisdom in quantum field theory, that one cannot uniquely separate orbital from spin angular momentum. So what has this to do with heavy ion collisions, which is the question we are interested in? Well, the point is the following. In relativistic heavy ion collisions, we usually assume in the hydrodynamic model that the system achieves a state of local thermodynamic equilibrium over some 3D hypersurface sigma naught, which is, in the Bjorken model, identified within a hyperbola with constant Milnor time. What is local thermodynamic equilibrium? Local thermodynamic equilibrium is a quantum state which is obtained by maximizing the entropy, minus trace rho log rho, with constraints. These constraints enforce the energy density, momentum density, the charge density, and the angular momentum density to be given. So that means that one assumes that these densities are known at some time. This is just the initial condition of a relativistic heavy ion collision, if you wish. The solution, so the state which maximizes the entropy with these constraints, is given in this equation on the bottom of the slide. This equation expresses the state of the system as a mixed state, as an exponential of over this hypersurface sigma naught. Omega lambda mu is a quantity, an antisymmetric tensor, which is coupled to the spin tensor, and it is named reduced spin potential just because it is adimensional. So this is a new naming I'm introducing. So in some papers, you can find this as spin potential, in others, spin chemical potential. From now on, I somehow propose to call it reduced spin potential because it is adimensional, so it is something divided by temperature. All right, this is not so sorry, I'm still having problem. Okay, now, what is the problem? The problem with this state, it is the following. It is dependent on the pseudogauge. So it is not invariant in form under a pseudogauge transformation, which was noted in this paper. So if you take this local equilibrium density operator, and if you change T mu nu and S mu nu with a pseudogauge transformation with some superpotential, what you will get is that this operator will change in form. For instance, from a canonical to Belinfante transformation, this operator gets changed in form, and it shows some extra terms depending on the thermal vorticity, which is the antisymmetric derivative of beta, and some terms depending linearly on the so-called shear tensor, which is the symmetric derivative of the fourth temperature vector. This is invariant only if the reduced spin potential is equal to thermal vorticity and psi vanishes. But these conditions are precisely that of the global thermodynamic equilibrium. So a system which is globally equilibrated, like the one, for instance, in rigid rotation. So in general, the local equilibrium is pseudogauge non-invariant, and it is invariant only if global thermodynamic equilibrium is achieved. And this is a problem because in heavy ions, we don't have a global thermodynamic equilibrium. We have just a local thermodynamic equilibrium. The consequence is that every measured quantity, the main consequence of this non-invariance is that every measured quantity, mean, spectra, fluctuations, in quantum mechanics can be written as the trace of an operator X with the density operator rho, okay? So the point is the following. All the operators that we are dealing with, spectra, V2, fluctuation, whatever, corresponding to measurable observables in relativistic heavy ion collisions are indeed pseudogauge independent. So there is no problem from the point of view of the operator. The problem is that the state is pseudogauge dependent. And so as a result, the mean, the measurement, is pseudogauge dependent, because which is expressed by this diagram. So rho is pseudogauge dependent, X is pseudogauge dependent, and as a result, the mean is pseudogauge dependent, in spite of the fact that the operator does not depend on the pseudogauge transformations. And an example of this is the polarization. It was pointed out in this paper by Matteo Buzzegoli that in different pseudogauges, the theoretical calculation of local equilibrium of the spin polarization has different forms according to the pseudogauge chosen. For instance, in the Belinfante pseudogauge, you have this result that the polarization spin vector of fermions is the sum of a thermal vorticity part, which is very well known, and the one which depends on the thermal shear. And this was mostly used in numerical simulation. But If you go to canonical pseudogauge, then you have an additional term, which depends on the difference between thermal vorticity and reduced spin potential, omega minus omega. Now, you may say, okay, assuming that omega is equal to, say, to the thermal vorticity, then this term gets canceled. All right. However, if you change pseudogauge and you take the one which was proposed in this book by De Groot, which is in literature is named GLW, then you get a different formula where the shear part is not even there at first order. So that means that the mean value of our prediction of the mean value of the spin polarization depends on the chosen pseudogauge. And this can be a problem. Why is it a problem? In fact, it is a problem because the local thermodynamic equilibrium density operator is just our assumption of the initial QCD plasma. So this is our initial assumption concerning the state of the system, concerning the plasma. But strictly speaking, the actual quantum state in the Heisenberg representation of the system we're dealing with are just the two colliding nuclei. This is the actual initial state. And this state is pseudogauge invariant because it just depends on two momenta of the nuclei. So in other words, we introduce a pseudogauge dependence because we made some special assumption about the initial state of the plasma and not the initial state of the collision. Indeed. Okay, now let us suppose, for instance, to switch from the Heisenberg to Schrödinger representation where the state is evolved and the operators do not depend on time, okay, for a while, until we get to the tau naught, which is the supposed time of thermalization. So if we evolve the initial actual quantum state in the Schrödinger representation, so if we evolve the initial two colliding nuclei, what we will get is something which is still pseudogauge invariant. The reason being that PA and PB are pseudogauge invariant state. And so is the Hamiltonian H. Therefore, the evolved state in the Schrödinger representation cannot depend on the pseudogauge chosen. All right. When we get to tau naught, the basic tacit assumption of the ion collisions is that we replace the actual state, which is unmanageable. So we cannot make any prediction because we cannot, say, solve the QCD Hamiltonian in real time. Okay, what we do is that we replace effectively this state at tau naught with a state of local thermodynamic equilibrium, which is indeed non-pseudogauge invariant. So what we do in our assumption is that we replace a pseudogauge invariant state, which is the actual one, with a non-pseudogauge invariant state, which is our representation of the state of the system in the initial condition. And this is where the, between quote, error occurs. Now, what should we do? In order to avoid this problem, what we should do is that we should replace the non-pseudogauge invariant local thermodynamic equilibrium with a pseudogauge invariant operator, so that our approximation, which will remain an approximation indeed, but at least it will fulfill the requirement that to be, say, more conformal to the actual state, which is pseudogauge invariant. So we should construct a local thermodynamic equilibrium density operator with the following requirements. First, minimal deviation from the known form. So minimal deviation from the form that we have already found by enforcing the densities of conserved quantity to be given. And this is a linear combination of the stress energy and spin tensor. Second, and most important, pseudogauge invariance. Third one, this form should reproduce the correct global equilibrium limit. So let's start from the first requirement. The first requirement, minimal deviation from the known form. So let's assume exponential form of an operator upsilon, which is given by an integral of a linear combination of stress energy tensor and spin tensor with some unknown, so far, numerical fields x, y, and z. What we do then? we can study what is the change under the pseudo-gauge transformation of this operator upsilon. So what happens is that if you change upsilon with a pseudo-gauge transformation, what you get is delta y, so delta upsilon, sorry, equal to this form. By taking advantage of some integration, some boundary term which vanishes and so on and so forth. So we have now an equation, and we have to enforce that both these coefficients should be zero in order for this integral to be zero, whatever the superpotential is. And this leads eventually to very simple equations and to the following form, which is the solution. The local equilibrium density operator, which is pseudo-gauge-invariant, is given now by this combination, T mu nu beta nu minus 1/2 thermal vorticity S mu du lambda minus, and this is the new one, a new term, minus a term which multiplies the shear tensor, the thermal shear tensor with the spin tensor. Omega mu nu and psi mu nu definitions are reported below the formula, just to remind you. Now, a posteriori, we can check that this form is indeed invariant under pseudo-gauge transformations. And now we are happy, because that means that our approximation of the state of the system does not suffer from this dependence. Now, this form has the peculiarity that whatever the spin tensor and whatever the stress energy tensor you choose, you will get the same answer. This is very important. You will get the same answer for all measured quantities. What are the consequences of this choice? Well, if you look at the previous formula, you see that now there is no longer have a reduced spin potential, which is coupled to the spin tensor. Now, the quantity which is coupled to the spin tensor are quantity depending on the four temperatures. So they are thermal vorticity and psi. So this means that with this operator, not only at the global, but also the local thermodynamic equilibrium, must the reduced spin potential be equal to the thermal vorticity. So in other words, with this choice, local equilibrium implies that the spin potential is always locked to the thermal vorticity. The second consequence is that one can choose, in the previous form, in this one, the Belinfante pseudo-gauge, where any choice is equivalent. So we can choose S equals 0, which is a Belinfante pseudo-gauge, and then so we have that the local thermodynamic equilibrium invariant form is just given by the integral of T mu nu Belinfante beta nu. And this has the implication that all correct spin polarization expressions, if you accept this new form, are those calculated thus far in the Belinfante pseudo-gauge. So if we go back to the slide where I show this formula, this one, the number one is the correct one. And the other two are ruled out by this new form. And now the question which someone, I think, already had in mind is, what about spin hydro then? Well, it looks like spin hydro is now immaterial with this choice, because the identity, if you accept the spin hydro is, if you think of, spin hydro as a theory of small deviations from local equilibrium, the identity, the spin potential, the fact that the reduced spin potential is locked to thermal vorticity deprives the equation of the conservation of angular momentum of any dynamical content. So in other words, this would be just a trivial consequence of the conservation of energy and charge, which should suffice to solve the dynamical problem. However, there is an issue here. So an open issue that I don't have an answer to it so far, that are the fields beta and zeta pseudo-gauge invariant if the stress energy tensor is changed in relativistic hydro? This is something that I cannot answer as yet. So this brings me just to directly to the conclusions. So in summary, we have derived the pseudo-gauge invariant local thermodynamic equilibrium density operator, which modifies the previous one, which was pseudo-gauge dependent. This entails that, so this choice so this form entails that the local equilibrium, the reduced spin potential is equal to thermal vorticity, so that any deviation of the spin potential from the thermal vorticity means that we are in a known local equilibrium condition. So I have told you about this, what are the consequences for the spin polarization expressions, and an open issue is, an open question is about spin hydro. So will spin hydrodynamics still be relevant? I think this is an open question with this form. I think, so I have finished. Thank you.
Thank you, Francesco. I have several questions.
All right, thanks. I really look forward to the paper. This looks really interesting. Two related points. I mean, the first one is that hydrodynamics wouldn't be a conserved current equation equation anymore, because the symmetric shear is not a conserved current. And also, and also one thing, I mean, the pseudo gauge, actually there is a physical sort of way to think about it. It's a coordinate transformation together with a field redefinition, which leaves the action invariant, sort of similar to angular momentum. You change coordinates and you redefine the field, but the action is invariant. So,
asking whether the pseudo gauge transformation can be seen as a coordinate transformation and a field redefinition at the same time.
Yeah. This was Thomas Browner has sort of shown this in
sorry?
a very nice paper. Yeah.
No, sorry, okay, so if you ask me if I know this, I don't know. Okay. So I don't know of any derivation of this. So if you mean that these transformations can be obtained, yes. If you ask me if this transformation can be obtained with a coordinate change in the field redefinition, I don't know. Yes, so if you know it, just tell me, because just send me the reference. And as far as the first question is concerned, sorry, can you say it again, because I didn't get it?
I mean, a lot of people think that hydrodynamics is a theory of conserved currents.
Yes.
But here it wouldn't be a conserved current anymore.
Why not?
Because the symmetric shear is not a conserved current, is not associated with any conserved current, right?
No, I mean, in fact, okay, so the equation of hydrodynamics would still be the same. Okay, the mu T mu nu and the mu J mu equals 0. All right? So the fact that, so I mean, in fact, you see that in these equations in this equation I put the arguments within a square brackets, because it means that this is a functional dependence. So T mu nu depends on beta, thermal vorticity, thermal shear, and higher order derivatives, if any. Okay? So the conserved current are the angular momentum current, the angular momentum current, the stress energy tensor, and J mu. Not so psi here plays the role of a coefficient multiplying the currents. So it does not need to be a conserved current itself. And in fact, this is the new thing. So the fact that in the local thermodynamic equilibrium density operator, it appears something which does not, say, vanishes at global equilibrium. But it's local equilibrium, so it is perfectly legitimate.
Hi, Francesco. Very nice talk. Actually, I was very glad to hear the final statement in your summary that is spinning hydro still relevant. I believe it isn't, and it never was. If anything, we should learn from solid-state physics. The only spin polarization people know about comes from magnetization. And the spin polarization will happen when you put it in a magnetic field, when you start rotating it, and then the only dynamical, truly important thing will be magnetization. And that's, I believe, the only degree of freedom you have to talk about. Spin by itself, decoupled from those two things, rotation or magnetic field, seems completely unphysical, and I think you are proving it.
sorry, I only partly agree with this statement. And the reason is the following. In condensed matter physics, we only have particles, all right? And so this is why that all spin phenomena are accompanied by or induced by magnetization. But in a relativistic quantum field theory, we have both particles and antiparticles. So we may have a situation in principle where we have polarization and yet no magnetization. Because you may say polarize particles and antiparticles in the same direction at the same time. Now the real issue to me is whether the spin tensor, the real issue is the fact that you can change the spin tensor and obtain, obtain a different theory and obtain a different description of the system. That was the problem. So, but I don't, it is, to me, for instance, I mean, the measurement of lambda polarization, for instance, proves that we have a polarization of spin polarization of the particles without having magnetization, possibly. Right? And that the point here is the role of the spin tensor. So, does the spin tensor play any role in determining the spin polarization of the particles? And I am now led to think that the spin tensor, so the modification of the angular momentum current, does not play a major role in this.
Okay. I guess this discussion will last for the next few years. So let us go.
Thank you.
For the last question, Kenji.
Hi, Francesco. So, yeah, it's a really interesting talk. And my question is very, very simple. So you showed the superpotential, but in principle, the pseudo-gauge transformation to the energy momentum tensor and that to the angular momentum tensor, they can be independent, right?
Why? Sorry.
Oh, because the point of the pseudo-gauge ambiguity is if you add something, then that also satisfies the equation of motion. And so you can independently add such trivially conserved quantity of the tensor structure independently to the energy momentum tensor and the angular momentum tensor. And so I think that superpotential form is a bit strong assumption. That is my impression. So can you clarify this?
Sorry, but I don't think that you can do this, because I mean, if they were independent, so suppose, for instance, that you change T mu nu, only T mu nu, right?
Yeah.
Okay, if you change only T mu nu, what happens is that then you can this form is general enough. But if you do this, then your angular momentum current has an orbital part, right? An orbital part will be changed, and the spin part will not. All right?
Yeah. Yeah. So yes.
And then okay, I think that you cannot really make it vanishing then. Sorry, you cannot make you cannot make the integrals non-vanishing.
For T and J conserved quantities, they can be the independently manipulated, and then okay, I don't know that separation.
No, Kenji, sorry.
Part and this.
No, what is implied in these equations is that the current J, all right, is defined as x mu T lambda nu minus x nu T lambda mu.
So probably you don't want to change the orbital part. That is your assumption. Is that correct?
So I mean that since J, the current J mu lambda nu, also depends on T, all right?
No. That is a relation you can find after all. And so you don't have to keep that relation. And so...
Okay. Now let me say this. In these relations that I showed, okay, it is understood that the angular momentum current is has an orbital part, which is x mu T lambda nu minus x nu T lambda mu. Sorry, perhaps I mixed up the indices, but anyway.
That is assumption, right?
Sorry, it is not an assumption. It is not an assumption. It comes from the Noether theorem. For instance, if you have a Lagrangian and you want to know what are the currents which generates the integrals which generate the symmetry, then you will always find the orbital part. That is granted by the Nefer theorem.
Okay, unfortunately, we have to stop the discussion here.
Yes.
Thank you again, Francesco. Okay, so I'll see you soon in the debate session.
No. No. What? This? No. Correct. How to? What?
This is like that, right?
Okay. Okay. So does it work? Yes. Yes. Okay. Okay. Huh? Oh yeah. Okay. Okay. Okay, so can I start? Yes. Okay. Okay, so thank you very much. I'm very happy to give the presentation about the spin potential issue. That is much related to what you heard from Maxim's talk and also the Francesco's talk. And in fact, recent years I'm working on some spin and rotation, and I'm pretty much rotating nowadays. So yeah, in fact, so this is extremely non-trivial problem, as you can already see from several talks. And in fact, I can safely skip the introduction part because the previous speakers actually gave a fantastic introduction. And in fact, the rotation is already very, very confusing. So let me start with the rotation in equilibrium. And in fact, so we started this kind of the business already since 10 years ago. And with my friend, Shugan Huang, so we actually pointed out some similarity between the rotation velocity and the chemical potential. And then Jin Feng actually wrote a very nice cartoon, not cartoon, but phase diagram based on some calculation. And then, so this is clear that the phase structure looks like the conventional QCD phase structure, but the only difference is the chemical potential is replaced by the angular velocity. So the angular velocity looks like the chemical potential. And in this case, so this is actually the phase transition in terms of the chiral sector. But the deconfinement sector, we also investigated using Hadron Resonance gas model. And then the conclusion was, if you rotate the system, then the symmetry is more restored, and so TC is pushed down. That is actually the conclusion from the model. However, if you see the lattice, the things are completely different. And the first lattice was formulated by these people, Yamamoto and Hirono. And so they actually measured only the angular momentum as a function of the radius from the rotation center. And so using this formulation, some people, Victor Braguta and the Maxim Chernodov and their collaborators actually did more sophisticated simulation, and they found that for imaginary rotation, the TC is pushed down, which means that for real rotation, TC must be pushed up. Is there any problem? Okay. Okay, so this is completely opposite statement to this model conclusion. And so this is actually, this caused a lot of the dispute in the community. So this is very unnatural, right? Because intuitively you may think that, for example, so this is actually as a function of the radius from the rotation center, the TC is pushed down. So this is an imaginary rotation. And so the TC is actually pushed up more and more. And so, but the point far from the rotation center moves at higher velocity, which means that it is Lorentz contracted, and so the TC must be effectively, the temperature should be effectively pushed up, and so TC must be pushed down. That is a natural intuition. However, what happens is completely opposite. Okay, so this is actually a very confusing point. And in fact, okay, there are some nice gradation is missing. I'm very sorry. So this is actually a very nice cartoon, but okay, the PDF has some problem. I'm sorry. But anyway, so several years ago, we did a PQCD analysis. So above TC, the part of the PQCD must be the reliable first principles calculation. And then we found that the polyalcohol potential has some singularity. And so, as I told you, for real rotation, the natural direction is TC must be pushed down. Okay, and so just like in the case of the finite density system, and so it is quite natural to expect that TC must be pushed up if you introduce an imaginary rotation. And what happens here is extremely non-trivial. That is, TC is pushed up to infinity. Infinity means that for whatever high temperature, you have actually the perturbatively confining phase in this phase. So that we found based on the first principles perturbative calculation, but this is completely different from the lattice simulation. And so that is actually a big problem. And just recently, we did also the alternative first principles approach, that is strong coupling expansion. And so we saw that this is a very minor subject, and so there must be no competitor. But surprisingly, the Chinese friend, the Ho and his friend, his student, and so they published actually exactly the same scheme and then a very similar approach. And so we are really shocked, and then we actually wrote the paper within one week. And then, so this is actually already accepted for publication. But anyway, so what we did was that at finite temperature, you can write down the polyalcohol effective theory from which you can actually describe the deconfinement phase transition in a very, very good way. That is perfectly consistent with what you see from the lattice simulation. So the strong coupling expansion is a very good approximation to understand the quantitative, even quantitative nature of a phase transition. And then what you should do is introducing such kind of funny shape of a bracket that is proportional to the rotation velocity omega. And in such a way, so we can resum all the diagrams, all the such contributions of the same order of the strong coupling expansion. Then we found that TC should be pushed up for the imaginary rotation. This is again completely opposite to the lattice simulation. This is same lattice setup, but the analytical lattice strong coupling expansion gives a completely opposite answer to the lattice numerical simulation. So I'm very puzzled about this interpretation, but anyway, we found that the rotating lattice has some artifact. This is a little bit technical part, but if you know the very famous argument by Hasenfeld and Karsh, the finite, okay, in order to introduce a finite chemical potential, you must be very, very, very careful not to break gauge invariance. And so in this case, as I told you, the rotation velocity is pretty much similar to the chemical potential. And so the same thing happens. And we found such a problem. And so maybe the lattice people must improve the lattice action. So this is actually one important message from this analysis. Anyway, so now the things are still very much controversial, and so there is no conclusion. But anyway, so what we need is some thermodynamics, including the rotation, some potential that I would call that spin potential, or but to solve the spin hydrodynamics, what we need is not really this full rotation, but some funny thermodynamic quantity that gives you the spin excitation value if you take the derivative with respect to the spin potential. This is what we need. And so the question is how to construct this. This information is essential to solve the spin hydrodynamics. Okay. So now I'm coming to the more and more out of equilibrium stuff. But anyway, as a preparation, I need such equilibrium the information. Okay, so this slide is already explained very well by Maxim, and so I don't have to explain this. But well, the angular momentum tensor you can write down, and then the spin part is gauge invariant. So there's no ambiguity to define this spin tensor. And then you can actually introduce a chemical potential, or not chemical, but anyway, the potential, some potential coupled to this quantity. And then, so this term is pretty similar to the axial vector current. And in fact, the Igor pointed out this. This is nothing but the separation between two wide points. But of course, I completely agree. But according to Feynman, of course, the same physics must be explained in 3 different ways. And so the Igor simply gave the second, the interpretation. And I would give you the third interpretation. That is, in fact, the theta derivative. So you know the chiral chemical potential. That is the essential piece for the chiral magnetic effect. That is actually the time derivative of theta. That is nothing but mu5. And so here, this coupling to the spin potential, this part, axial vector, is nothing but the spatial derivative of theta. Okay, so if you have space-dependent theta, then that is nothing but this axial vector potential. And so that is my third explanation, okay? Anyway, in all the way, so you can get this dispersion relation that so you have already seen in the talk by Ricard on Monday. And anyway, so this thermodynamic property is quite complicated, very much different from the rotating system. That is because the Hamiltonian and the spin do not commute. Okay, this is a very different situation from the introducing the total angular momentum. Okay, so that is the reason why this dispersion relation is such non-trivial. And in fact, as pointed out by Igor, this axial vector potential, or the omega spin potential, is nothing but a separation between two wide points that you can induce, for example, by putting the circularly polarized light to the Dirac same metal that we already pointed out with my condensed matter colleague 10 years ago. But anyway, this is a quite well-known phenomenon. And also the more non-trivial question is, so this is so far the discussion was about the fermions, but the gauge sector, okay? The gauge sector, this is more non-trivial. And then the Maxim and I are now completing a work. And so if you see the angular momentum decomposition, it is of course not gauge invariant, not so clear how to extract the spin part from the gauge angular momentum. But this is one way. This is the decomposition proposed by Jaffe and Manohar in the context of the spin crisis, proton spin crisis. And if we adapt this, it is likely that this part without any spatial derivative must be the polarization, the helicity of the carried by the gauge particles. And then this E cross A is actually that you can find the very similar term in the Chern-Simons current. That is, if you see E dot B is the topological charge density, right? And this is actually a total derivative of some current. And this zeroth component is nothing but a magnetic helicity, okay? And so there are many people are talking about this magnetic helicity, but the spatial component is nothing but the spin potential, the spin of the gauge particle. And so it is quite natural to speculate that the spin potential must be introduced in such a way using this Chern-Simons current. And what is the benefit? The benefit is, in this way, you can actually introduce the quantity in a gauge invariant way. That was already pointed out by Valery Rybakov many, many years ago when everyone was confused about the interpretation of mu5. And he actually pointed out that mu5 is nothing but the coefficient in terms of in front of the topological term. And so our prescription is completely consistent with his proposal. And so what we say is that this spin potential is nothing but the theta space-time derivative, and that is coupled to the Chern-Simons current. And so the zeroth component is, of course, the physics of CME. And now we know how to use a spatial component. That is the introduction of the spin. So by injecting spin, you can actually see not only the temporal part, but also the spatial part of the topological sector in QCD. This is really the new challenge to see the topological property of QCD. So this is quite interesting. And okay, I can skip this, but anyway, okay, this is actually the dispersion relation you can obtain in the same way as this computation. And then, in fact, that dispersion relation is somehow known in the different context. That is the Casimir effect. Frank Wilczek and his student actually published a very interesting paper that usually the Casimir effect is attractive, but if you have some funny background, then this could be a repulsive interaction. And we found that with this dispersion relation, the Casimir force is actually repulsive. So in fact, this dispersion relation is known in some contexts. But anyway, so in such a way, anyway, the static thermodynamics is already extremely non-trivial. But now let's come to the spin dynamics. That is out of equilibrium part. Okay, but so Igor was very negative about the spin hydrodynamics, but now let me give you the answer, okay? So that is, we are interested in the fate of dynamics of a spin, right? And so what is the dynamics of spin? Of course, we know that if you put the magnetic field and spin, of course, what you can expect is a spin precession, right? And so that you may think that if you put magnetic field and spin, the spin must be aligned to the magnetic field, but this is not true. So for this, you need to introduce relaxation. Otherwise, so you just have the, the precession, that's all. And so you must introduce some relaxation term, and the Landau-Lifshitz introduced this term by hand, that was 1935. And also the Gilbert actually made the approximation because this term S cross B looks like this first term that is more dominant, and so it is a good approximation that this can be replaced by the left-hand side of this equation of motion. And so this is actually a quite well-known phenomenological equation to describe the spin relaxation, okay? But this is not yet satisfactory because this is not covariant. And so what is a covariant extension? That is actually quite well known. But to discuss that, the spin definition must be extended to the covariant way. And usually the Pauli-Urbansky vector is a very nice definition. And then from that, you can see that this Frankel condition must be satisfied, okay? So this is the fluid velocity, and then S dot U is 0. Okay, using this Frankel condition, you can prove that this is actually, okay, you don't have to care about this part. This the half part, the half upper part is a derivation, okay? But anyway, what I want to say is that using this just as a second line calculation, you can actually get this very nice, the relativistic extension of the spin dynamics of the equation. Okay, this is called the BMT equation. And so this first term is a relativistic term, the correction, and also you see this second term is a precession term, that is a B cross S. And also you must have some dissipative terms, but usually this is not really discussed in the context. But now, okay, let me show you the spin hydro derivation of this, and our conclusion is if you see the spin hydro, then you can actually derive the very nice spin equation of motion that has perfectly the consistent term with the relativistic term in the BMT equation, and also the spin precession. That is not a B cross S, but omega cross S, okay? The B is somehow replaced with the spin potential. And anyway, you also have some dissipative term. This gamma is some transport coefficient, and also several new terms, new hydro terms, the correction. This is our conclusion, okay? So now, by the way, so I use some funny expression here because so this one is actually the vorticity, and in equilibrium this should approach to this one, and so this term is gone in equilibrium, and this is shear term, and also the bulk term they are gone, and so only the precession remains. Okay. And so, this is anyway my conclusion, okay? So now for the rest of my time, maybe I have 10 minutes or something, yes? 5 minutes, okay. But now that I already gave you my conclusion, so I'm happy to stop anytime, anyway, okay? Oh, no, not yet, not yet. No, okay? No, okay. So, yes, I would be happy, but I wouldn't stop, okay? So, okay, here, okay. 2 minutes? Okay, 3 minutes. Okay, so in fact, the starting point is this one, okay? So from this, the expression for the angular momentum tensor and energy momentum tensor, you can prove this. This is completely the robust equation, and this describes, of course, the spin dynamics. And then the point is that if you use some Israel-Stewart the construction of the entropy principle, then you can actually express the entropy current and the divergence of the entropy current, that is entropy production. And entropy production must be non-negative. From that condition, these guys actually wrote down a very nice expression that is anti-symmetric part of the energy momentum tensor. That is this spin source. Okay, the spin source term must be given by this expression. This is very intuitively understandable equation. That is, this term is the difference from the global equilibrium. Okay, in global equilibrium, this is 0. Okay, from this condition. So you have two transport coefficients here and here. Okay. But now what I want to say is that, okay, so there are actually several references, but what I want to say is that it is more physical to consider that the spin tensor must be given in a completely anti-symmetric form. Then you can actually drop the 3 boost part. Boost generator is not Hermitian, and so the 3 rotational part is Hermitian, so this is only observable. And so by using this, so you can actually write down some corresponding equation. And in principle, these guys must have done this. But this is extremely complicated paper. And so I asked the question to Masaru, you must have written some equation corresponding to ours. So I want to make the comparison. But he said that, oh, no, our formulation is too complicated, and so I cannot make the comparison. And so I gave up. And then I asked this question to the Matthias, but Matthias promised me to give a reply. Oh, this is a very interesting question, and so I will reply next week. But there is no reply from Matthias at all. But anyway. So okay, now, okay, the time is running, okay. Now I have actually, because of this, I have several extra terms, and those extra terms are extremely important. Then those extra terms can be absorbed into several extra contribution to the heat current, and also this phi mu nu, etc. And then I get this new equation. Okay, so this is very similar to BMT, but some corrections. Okay, now this is my summary. So the spin hydro is useful in this way. I don't know whether the Igor was happy or not, but anyway, this is one useful way to use spin hydro. And of course, the phenomenological application is quite interesting. We are working on that. Thank you very much.
We have time for one question, hopefully short. We have discussion session in the afternoon, so this is not the only. Sure.
So I have a short question. So why in your page 19, why does spin couple to bulk tensor? The last term.
Where?
The term under precession, the bulk term. Why there's a dissipation caused by partial dot u?
Partial dot u.
Yeah. The last term.
The rightest term of the second line.
Oh, this one?
Yes. Do you have an intuitive picture?
No. No. So these new terms are completely missing in the literature. So this is completely new. So I don't know. Maybe there must be some interesting, yes.
Okay, unfortunately we have to continue because we're sort of really late. Thank you very much.
Thank you.
Next speaker is, I believe, Cicero Muncinelli / Jun Takahashi. Yeah.
Okay.
Sort of.
Can you hear me?
Yes.
Yeah, okay, thank you. Let's just...
Okay, good.
Okay, can I go ahead? Okay, so good morning everyone, my name is Cicero, and today I'd like to talk to you on behalf of these 3 gentlemen here in the slides, which are also attending the conference with us today, and I'd like to talk about lambda polarization as a probe of jet-induced vorticity. Or in other words, how jets thermalized in the QGP induce vortex rings inside the QGP, and those in turn polarize lambda hyperons. So just a quick outline of what we will talk about in this presentation. First, I like to talk about the object of interest that we're going to analyze, which are the QGP vorticity rings, then a hydrodynamic model that we are going to use to model those rings and simulate them. Then how do we correlate vorticity and polarization? Then how we measure that lambda polarization experimentally, and how can we correlate the polarization to those vorticity rings and their shapes with something we call the ring observable. Then lastly, we're going to develop this ring observable and get some of its properties and probe some QGP properties using this ring observable. So this is going to be more of a phenomenological talk than the previous ones. So first of all, what are we talking about, those QGP vorticity rings? Say you had a hard interaction in the middle of one of your heavy ion collisions. Well, from one side, you had an unquenched jet, and from the other, say you had a partially quenched jet. In the same way, we would expect the formation of vertical toroidal rings, so smoke rings, from everyday fluid dynamics, say from someone smoking. We can expect the formation of the same kind of ring-like structures inside the QGP due to those partially quenched jets in the plasma. And how do we model those kinds of rings? Well, first we have Trento, which is an initial condition generator in 3 dimensions, and what it gives us is essentially an energy density profile for each initial condition in 3 dimensions. Then we plug that initial condition inside music, which is a 3+1 dimensional hydrodynamic evolution software, and inside music we also insert a high momentum bullet, say coming from a thermalized jet, inside the initial condition that is going to be plugged and evolved hydrodynamically. And by doing so, we can see the formation of those ring-like patterns. Here we have a jet going in the x-axis direction. The vectors represent the fluid cell velocities, and the color represents the vorticity we have induced by that ring-like pattern. Then to top it off, we use ISS, which is a hypersurface sampler that does hadronization, and the vorticity spin coupling that we are going to use to calculate the lambda polarization. So we know that vorticity induces polarization, and thus that polarization carries vorticity information. But how do we correlate those two? Well, first we define thermal vorticity for each fluid cell in this way right here, so essentially a function of the 4 velocities of the fluid cells and the temperature. Then we can calculate the min spin 4 vector of each lambda particle in the hypersurface, essentially by taking this weighted average here. And finally, we can get the lambda polarization 4 vector by simply dividing by the mean spin vector here, which is half for lambda. So essentially multiply by 2. Then how do we measure lambda polarization? First, I'd like to answer why we would use lambda hyperons instead of, say, other candidates. First, because lambdas decay weakly, and thus they have an anisotropic decay distribution for their daughter particles. So essentially a decay constant, the magnitude of the polarization in the lambda's own rest frame, and the cosine of the angle between the lambda polarization vector and the daughter momentum vector. Why lambda instead of, say, psi minus, which would still have those kinds of properties here? Because the lambda has a high decay parameter of about 0.747, while psi minus would have minus 0.4. So we have a high decay parameter, which makes this more anisotropic and easier to detect. The lambdas have a spin half, so we can describe their polarization by the mean spin vector in the way we did in the previous slide. And finally, they have a single decay vertex. They mainly decay into a proton and a pion, so it's easier to measure these kinds of decays. Then how do we retrieve from those daughter distributions the polarization of the lambdas? Well, for each particle, we can say that the mean polarization along an arbitrary quantization axis, which is n hat here, it can be x, y, or z, thus we can recover the 3D polarization vector, is given by an average of the projections of the distribution of those daughter particles of the decay. then to take this, which is an average on each particle's decay, into an ensemble average, we can just average over physically equivalent particles in the same transverse momentum, rapidity, phi, and this is the distance from the angular aperture from the jet. So here we have this kind of formula for the main polarization. But then we need to boost that polarization vector, which is defined into the lambda's rest frame, into the laboratory frame to calculate what we will call the ring observable, to measure the vorticity in those ring-like shapes. But there's a problem. To boost the polarization into the laboratory frame, we would need to know the lambda for vectors so that we can construct the boost matrix. But we lose the identity of each lambda and thus the form momentum of that lambda when we take these averages on physically equivalent particles. We can't recover the polarization for each particle, but the polarization for a set of physically equivalent lambdas. To go around that, what we can do is define a mean for vector for those lambdas inside the transverse momentum, rapidity, and phi bins. Then we construct that kind of mean for vector and then boost the polarization in the res frame into polarization to the laboratory frame. Okay, so now that we have polarization, how do we correlate polarization with that kind of vertical structure we are trying to understand? Here comes in hand the ring observable, which we define as this kind of average here. So we essentially are projecting the polarization vector in the direction transverse to the jet propagation. And this essentially measures the component of polarization circulating the jet. And this is a signature of those smoke rings, because we would also expect vorticity to encircle the jets if we have that formation of ring-like vortices. So this is a signature of the smoke ring. So to better understand what this ring observable can give us, what we can retrieve of information from it, I'm going to start by analyzing a very simplistic bullet that we can inject inside the QGP. This bullet will be injected in the center of the fireball. We will take transverse bullets only, so a mid-rapidity cut here, in a way that we can describe the injection of the bullet using only one angle, which is the azimuthal angle. We're also going to uniformly sample the direction at which we are going to inject those kinds of bullets with this phi j angle here on the initial condition of the evolution. And by doing so, we have these kinds of signatures here. And what you can notice in this plot first is that we have two very different kinds of two families of plots, the blue and the red curves. And the red curves, which are the true values, so to say, are event-by-event simulations. So we take an initial condition and we inject a bullet in that initial condition, evolve it, and then we extract the ring observable. There's also a useful approximation that we can do, which is to average over, say, 10,000 different initial conditions, thus getting these kinds of smooth initial conditions. And then instead of running 10,000 different initial conditions, each one with its own bullet, its own jet evolving in the QGP, we can then use 250 different jets inside this smooth initial condition. So we evolve from that, which reduces the need for statistics to consider, say, effects from the anisotropic expansion of the medium. Well, after that, what we can also notice is that this smooth initial condition approximation works well enough. We can kind of reproduce the same profile and the same magnitude, and it's easier to compute. We also have a clear distinction between the signal of the with jet events, which are these solid curves here, and the no jet events, which are these dashed lines here. And more interestingly, those background-like events here, where we have no jet, so we shouldn't have the formation of any of those QGP rings, have a signal that integrates to zero. And we can understand that as the polarization that is caused due to the expansion on the reaction plane angle, so expansion due to the the polarization due to anisotropic expansion of the medium averages out with the random choice of this phi j trigger direction. In other simpler terms, we can say that in the same sense that we could fix the reaction plane angle and then inject jets all over azimuth, we can symmetrically fix a jet direction and somewhat sample over reaction plane angles in all possible directions, and that would average out the effects of the anisotropic expansion of the QGP. Thus, we have for those true values E by E events a signal that is 0 within error bars, and for the smooth initial condition approximation, for which we don't have the capability of averaging over those reaction plane angles and thus having a 0 background, we see this kind of background signal on the blue dashed lines. But an interesting thing to emphasize is that still this has a 0 integral, and this will be interesting later. So we can make this a little bit more realistic. Instead of injecting the bullet inside the center of the fireball, we can make the radius at which we insert those bullets free. Of course, still keeping those two cuts and variations that we had earlier. Well, when we do so, we have an extra liberty, so to say, and we can separate our events in two kinds of jet injections. So jets that are going outward, going along with the flow of the expansion of the QGP, and jets that are going inward, so against the flow of the fireball expansion. Well, the first thing I'd like you to notice is that the external bullets, which are these ones marked by arrows here, have a higher signal than the other ones that were injected closer to the center. And that happens because the external bullets have less time to dissipate, so the bullet has a higher velocity, and we have higher gradients of velocity, which in turn induce higher polarizations, higher vorticities, and then higher polarizations, and finally stronger ring observable signals. Then another thing we can notice is that by depositing with the flow or against the flow, we also have a different magnitude of the signal. By depositing against the flow here in the right-hand side plot, we have larger velocity gradients in the QGP, then larger vorticities, larger polarization, and we have a signal that is higher than if the same bullet was injected going outwards. Another interesting thing we can get from this is that the angular aperture, so the distance between the two peaks of the ring observable, is a proxy for ring size. Say we looked at the most external bullet going outwards. It has less time to develop, less time to expand, then it is more centered on the direction of the jet. It's closer to the jet in aperture. So we can use that angular peak distance as a measure, as a proxy for ring size. Then we can even go a step further and do an even more realistic bullet that not only has free radius at which we inject the bullets, but also we mix events that had bullets in the center with events that had a bullet more external, which is closer to what we'd have experimentally, where you don't exactly know where the hard interaction happened in terms of radius on the QGP. When we do so, we have these kinds of structures here. So notice we lose those double peak signals that we had earlier because different radii have different angular apertures of the ring observable. Then we are essentially summing over all those ring observables from the last plot, and we lose that kind of double peak signal. But still, the integrated signal is consistently 0 for background events and non-zero for the with jet events, which are what we're trying to analyze. And another thing that I haven't talked about until now is that the signal also increases with centrality. In the left-hand plot, we have a central collision, and the magnitude of the ring observable is 0.06%, while in the right-hand plot, which is a more peripheral event, we have a ring observable in the order of 0.5, so a whole order of magnitude more signal than we had for central events. And that happens because in peripheral events, we have a shorter-lived fireball, and then the bullet has less time to dissipate in the median, less time to evolve. We have higher velocity gradients, and then higher polarizations and higher ring observables. So what else can we do with this kind of observable? We can probe QGP properties using polarization, using the ring observable, using the integrated signal and see how it varies with QGP properties. One interesting property we can vary is the shear viscosity of the QGP. So as you can see, with increasing shear viscosity, the integrated ring observable diminishes. That's because with stronger vortex ring dissipation at higher viscosities, the bullet dissipates faster, the velocity gradients are smaller, and then we have smaller polarizations. We also have sensitiveness to bullet velocity, so a jet property. If we keep the total energy of the jet constant and then vary its velocity in the medium, we also see that the gradients change, and we have a higher integrated observable as we increase the jet velocity. So maybe the integrated ring observable may act as a possible guide to furthering jet medium interaction models. And then to summarize this and give a bit about what we plan on doing, well, we looked in a new way at how the medium responds to thermalized jets, which is by inducing those kinds of vorticity rings that we measured with the ring observable. And that observable also decouples the anisotropic expansion contribution to the polarization of the lambdas from the jet thermalization contributions. So we can effectively remove this anisotropic expansion and look at just what we wanted to do, which is the jet thermalization contribution to polarization. We also have seen that it is sensitive to medium properties, such as the specific shear viscosity of the QGP, and that it is sensitive to jet properties, such as the position at which we inject those bullets, the alignment, if they go against or following the flow of the fireball expansion, the velocity of the jets, and we have also seen that it is possible to experimentally reconstruct the 3D polarization vector of those lambdas. One other interesting thing that is important to mention is that the predicted signal of the polarization is of the same order of magnitude as the global lambda polarization that was already measured by Starr and Ellis. So this should be a feasible analysis in the close future. This will be proposed to the Ellis collaboration soon. I myself and Professor Takahashi are part of the Ellis collaboration. We haven't still submitted the analysis proposal, but please stay tuned to a brand new vorticity measurement in the close future. And that's about it. Thank you, and thank you for your time.
Thank you very much. You're really early. This is very unusual in this. So we can answer questions.
Oh.
Please.
Thank you, Cicero. Very nice talk. I have two questions. One of them is very naive. So let me start with the naive one. I guess this observable or this mechanism will not contribute to global polarization just from the geometry that you just showed. It's something that is circling this ring, right? So zero contribution to global polarization in first approximation, I guess.
Yeah. No, please go on.
Second, in your proposal that you're going to submit to Alice, have you considered looking at P-A collision? In other words, P-lead collision. Because in this way, you certainly don't need a jet. You just have a bullet already going through. Excellent mind. So you stole my idea. Okay, so you are considering that, I guess, right?
Yeah.
And third, at very low energies, where we see that the global polarization peaks, I suppose this has nothing to do with global polarization, the measure, right? Because otherwise, it would, I mean, this contribution is zero, basically. Do you agree with that?
So sorry, you mean that at low collision energies?
Small square root of S energies.
Oh, okay. And sorry, could you repeat the?
At small energies, this polarization, ring polarization observable, has nothing to do with global polarization. Because there are no jets.
Oh, no. We are not talking about global polarization comes from the from the initial shape of the collision. So it will come from the angular momentum that you have from the two incoming beams. In this case, you are looking more at how the jets induce those kinds of polarizations. So not the anisotropic expansion nor the global angular momentum. So yeah, it's separate.
Okay. So in your simulations, you showed also a large signal when there are no jets, in particular for peripheral collisions. So in this case, how do you interpret the signal without jets? Just rings forming naturally, or?
Okay, so we're talking about, let's say this plot here. So in this case that we have no jets, what exactly do we define as the jet direction, so to say? Here in this case, we define for the smooth initial condition, say, the blue dashed curves here. We define what would be the trigger jet direction that we're going to compare as the reaction plane angle. So we are looking at the vertical structure that is introduced by the anisotropic expansion. So this also could measure that kind of polarization, that kind of vorticity ring structure that comes from the anisotropic expansion. So not necessarily from jets. It also measures other kinds of vorticities along an axis.